Hi, everybody. This is Ben Hopkins. Today's session is Ker SPLAT Overhauling World Interactions in Cosmonious High. A little bit about me. My name is Ben Hopkins. I am an expert graphics engineer at Owlchemy Labs. I've been working at Owlchemy Labs now for over 6 years. I've worked on all of our virtual reality titles, including all internal ports for PlayStation VR and Quest. Myself, I have 25 years in games and interactive coding. My first language was Z80 assembler on the original Game Boy. And my day-to-day languages are C# and HLSL, with some C++, Java, Python, for things like native plugins, tooling, and some of the R&D work that we do at Owlchemy. So a little bit about Owlchemy Labs. We were founded in 2010 and have been exclusively making VR games since 2016. In 2017, we were acquired by Google. And we make absurd and highly polished games with a big focus on hands and physics interaction. Our motto is VR for everyone. So our VR games include Job Simulator, Rick and Morty Virtual Reality, Vacation Simulator, and most recently, Cosmonious High. And that's what I'm going to be talking about today. So Cosmonious High was released earlier this year in March on both PC and Quest 2, and that was a simultaneous launch for us. And in Cosmonious High, you play as an alien species called Prismy, and it is your first day at an intergalactic high school. Main gameplay in Cosmonious High revolves around unlocking and interacting with all of your alien powers. And these include things like fire and fluid and ice and wind and telekinesis and resize. As you can see in the video on the right here, you can expand various objects in the world. And this talk is going to focus on SplatTech, which is our internal system for dynamically painting over the world, and how we got that running on the Quest 2, which was not a particularly easy task. So the initial implementation of SplatTech, the requirements were we needed multiple substances, things like water, paint, fire, and ice, basically all of the substances that would come from your alien powers. And these substances need to be able to cover all surfaces, both static and dynamic. So we have things like doors and drawers that the player can interact with, and then things like these plants that you see on the right here that expand when you water them. And so all of these things need to be splattable as well. And splats need to be subtractable. We have water, and water should be able to clean other substances that are being placed on the world, and it should be able to evaporate just like water does. So the obvious first step would be to store these splats and textures. All of our splattable objects in the game have unique UVs, so every triangle has space in the texture with no overlaps, meaning that every position on the surface itself can have a unique texel. And we need to be able to parameterize these substances, so come up with a group of parameters to define each of the substances in the game. And ideally as few parameters as possible, because more parameters means we need more textures to store them in. And then finally, once we have these parameters stored in textures, we can then sample them at shading time. And this will give us the parameters for the substance at the fragment level. So obviously, one of the issues with storing these in textures is that we want to have high detail, which then wouldn't require particularly high resolution for the textures themselves. So one of the ways that we can get around this is by using signed distance fields. SDFs are used in things like TextMesh Pro's font rendering, and they allow you to create decent silhouettes from fairly low resolution data. So we can store the SDF along with other substance parameters directly in our textures. So splats have a position and a radius, i.e. splat is essentially represented by the SDF of a sphere. So when we run our update shader, we calculate the world space position for geometry, calculate the distance to the center of each splat sphere, and that gives us the SDF. And then to integrate that with the texture, we simply use the min function to take that new SDF and figure out what the minimum value is compared to the previous value in the texture. And so from there, we can then create a mask by using a threshold operation on the SDF values. This allows us to create a nice silhouette. And of course, we can then use some noise stored in textures as well to erode away the edge to give us a nicer kind of high frequency detail along the silhouette of the splats. And since we're using a texture for noise, we can store different types of noise in the RGB channels, and then potentially even blend between the noises based on some of those substance parameters to control the shape of the splat based on the substance. So what about evaporating splats? For those who use another SDF, we refer to this as dynamic SDF versus the persistent SDF. And we store that also in the texture along with the persistent SDF and the substance parameters. And so when we update these textures, the dynamic SDF subtracts from the persistent SDF. So anything that's marked as dynamic will be able to subtract away the persistent substances. So in this case, we have water that is represented by the dynamic SDF, and other substances are in the persistent SDF. And the dynamic SDF evaporates over time by simply adding a very small value to it in the update shader. So over time, the distance represented gets farther away. And so when we do the threshold to create the mask, it starts to shrink over time. So our final data is stored in two textures. In texture 1, we have the persistent SDF stored in the red channel, the dynamic SDF stored in the green channel, the wetness parameter stored in the blue channel, and the thickness parameter stored in the alpha channel. And then in texture 2, we store RGB for the color of the substance and alpha for the opacity. So how do we go about updating these textures? So we have a component called Splatable that we place on any object that should be able to receive splats. And that component stores a list of colliders that are representative of that object. So generally the same list of colliders that we use for physics in the game. And so when we want to add a splat, we generally do that as a result of a collision from the physics system. And then we can take the collider that we collided with and do a lookup to find which splatable is associated with it, and then add that splat and its parameters to the splatable's internal list. And then each frame, when we want to update the textures for all of the objects, we find all of our splatables that have needed an update in that frame. From that, we now have a list of splats that should be added to their splat textures. And so what we do is we render the object's mesh using our special update shader. We pass splat parameters, so position and radius and the other values for the splat into the shader via float for arrays. And in the vertex shader, we take the UV coordinate and use that instead of position. And so what this does is rather than rendering the geometry in world space, we're now rendering the geometry as its UV layout. And so we read the previous splat textures so we can get the currently existing SDFs and parameters. And then we integrate the new SDFs that have been passed through the shader with that. So calculating the distance to the geometry and using the min function on whatever was there for that texel. We also interpolate the other parameters, and this is just a simple lerp between the wetness and the thickness and the colors. And once we're done with that, we have to run a dilation shader because otherwise we get seams. So we run several passes of dilation on the resulting textures, and finally we're done. And we can pass those splats back to the object's actual renderer material. So when it comes time to render the splats, all of our object shaders themselves have the splat shading code directly in line. So first of all, we run all of our usual code for calculating the color for that fragment, just for the surface. And then we calculate what the shaded color for any splats that may be at that fragment should be as well. So we basically calculate a weighted noise using the aforementioned noise texture and using parameters to interpolate between them. We then use that to erode away the SDF. From there, we can create a thresholded mask that will now represent the silhouette of our splat. And then we use the calculated noise to also generate a fake normal and do things like attenuating lighting and reflections using wetness parameters, etc. And so finally, we have both the surface color and the splat color, and we can simply blend those together to get the resulting output. And it works on PC. So MetaQuest 2. First time that we ran a build on device, we were looking at less than 10 FPS, which is not great. And the APT, which is the amount of time that a frame is taken to render on the GPU, was saying 65 milliseconds, which is also pretty alarming. Even more alarming is OBR metrics, which we use to get these kind of values out of the Quest, caps out at 65 ms for APT. So the chances are we were significantly over that, which is very, very bad. So what's slow? What can we do about this? First off, there's lots of textures. Every object that's splatable has 4 separate render textures. We need 2 to store the actual splat data itself. And then in our update shader, we need to be able to read the previous values. So this means we have to essentially double buffer. There's lots of draw calls. Each object itself requires several draw calls to update, both running the update shader and then doing the dilation pass. And there's lots of loads and stores, which is definitely something that you should avoid as much as possible on Quest. Anytime that you're rendering to an off-screen texture and then having to read that back, there's quite a bit of overhead there. And the dilation shader itself requires multiple passes per object, so that's a big problem for us there too. And there's a heavy fragment cost. As mentioned, all of the actual splat shading itself is happening in line in all of our shaders for the objects that we're rendering. And so everything is very, very expensive when it comes to shading time. And as a result of this, overdraw is a huge issue. Overdraw is something we fight with a lot as we're a forward renderer. And so the fact that all of our shaders are particularly heavy because they're also having to shade splats means that overdraw is even more of an issue. So basically everything. So what was our final implementation? And what do we need? The ideal case would be to generate a single splatable mesh for geometry around the player. With this, we could restrict updates for every frame to 1 draw call and 1 update. We could also control how far from the player we want to pay for splat shading. So if we want to limit to within 10 meters from the player, anything beyond that, we're not going to be paying a cost for. And if we take this mesh and render it less, then we essentially get a depth pre-pass. So no more splat shading costs from overdraw, which would be great. And the cool thing about this is we use teleport in our games. So we only really need to update this mesh technically when the player teleports. When we teleport, we fade the screen to black for a fraction of a second. And so that actually gives us some time that we could be doing some of these things. Ideally, also, we could reduce the 2 splat textures to 1. This would improve bandwidth both during update and shading. And theoretically, we could bit pack those 8 parameters into 32 bits. An example on the right of how we could potentially do that. And it would be really great if we could figure out how to speed up this dilation shader. This is something that we can't get around. We have to be able to fix the seams. So dilation is absolutely necessary. So we need to find a way to do that fast as well. And finally, do we actually need to be updating splats at frame rate? There's a good chance we might be able to update the splat textures at a lower frequency to the main camera. So first off is the splat mesh volume. The first thing we do is we collect all splatable geometry in the scene, shown here color-coded by different unique objects. And then we're going to cull triangles outside of a 10-meter radius. So everything that's 10 meters from the camera, we can get rid of. And from that, we can create a single combined mesh. So this isn't just a simple mesh combination. It's actually stripping triangles away that aren't necessary. And because we've started with many separate meshes that have all been unwrapped to their own 0 to 1 UV space, ideally we need to actually dynamically pack the UV islands into the texture for this generated mesh. If you think about simply rectangle packing for each of the unwrapped meshes, but some of those meshes are going to have 50% of their triangles cold, that means that 50% of the UV space is going to be wasted when we pack those just as basic rectangles. So ideally, if we could repack dynamically via the islands, that would be great. So the first step is, how do we find the UV islands? UV islands themselves split geometry. So an island can be thought of as a subgroup of interconnected triangles. So if you look at the example on the right, we have a sphere here that has a UV layout that's essentially 2 halves of the sphere. And for that to work, it means that at the data level, it has to actually be split. So we can take a triangle and work our way out, looking for its neighbors and all of the neighbors of those neighbors, and keep doing that until there are no more neighbors left. And at that point, we know that we found a separate UV island. And we can do this until we have no more triangles left, and now we have all of the separate islands. The problem with this is mesh assets themselves don't actually contain adjacency info. They're basically just a list of attributes and indices representing the triangles. So we have to figure this out for ourselves. The way that we do this is we go through creating a map for every index, and then how many other shared triangles reference it. And that is a good kind of building block to then work for figuring out kind of other adjacency information from there and running some of these algorithms. The problem with that, of course, is geometry can be split for reasons other than the UV layouts itself. So taking the previous example, we've now split the top part of the sphere. And as you notice with our previous trick, now it's only giving us half of the UV island because the geometry itself is actually split. So we really need to handle this case as well so that packing is optimal. And the way we do this is we just look for identical vertex attributes and consider those to be essentially shared indices. So packing islands to a single texture. Now we have all of our islands split up. We can sort them based on their bounding box in UV space, largest first. And then we can use a binary tree to pack those islands into our texture. So largest goes to the bottom left, and then it basically fills out from there. And one thing that you can do is calculate the convex hull for each island. And from that, you can then use the rotating calipers algorithm to figure out what would be the optimal bounding box. If you look at the example on the right, we basically go around each of the edges, figuring out the bounding box that is flush with that edge, and the smallest bounding box that comes out of that. The rotation of that bounding box would be the rotation that we would like to have the optimal bounds. Unfortunately, we didn't actually end up shipping with this, as in our case, this causes data loss due to the way that we're sampling. So what about movable objects? As mentioned, we have lots of things in the game that can move either via animation or the player interaction, and those should all be splatable as well. So the trick here is that we move the splat instead of the object. So for any splatable, we have a toggle that says whether it's movable or not. And if a splatable is marked as movable, we store its origin. So that's basically the place that it starts at the beginning of scene load. And then we can just inverse transform the splat position into that space. And as shown in the example on the right, the cube is rotating, the sphere is what's adding splats, but the wireframe shown below it is what's actually happening under the hood. So the cube doesn't move, we're moving the splat to the correct spot. The problem with this, of course, is that if we are moving the splat position, there is now static geometry that is not moving, and so the splat position is now incorrect for that static geometry. The way that we get around this is movables have a unique ID, and when a splat hits a movable object, we store that unique ID with the splat. And then when it comes time to actually update the splat textures, we compare the ID for the geometry with the ID of the splat, and if they don't match, then we skip it. So this means that a splat that hits a movable can only ever actually splat on that specific movable when it's updated. And finally, movables actually do use a separate mesh outside of the splat mesh volume. We don't have too many movables that are ever within the 10-meter radius at one time, so this actually ended up not being too much of a rendering overhead. But their UVs are still packed in with the static mesh's UVs, so they all share the same space and the same texture, and can be updated all at once without needing multiple draw calls for that. So how do we make this fast? The first step is to calculate as much as possible offline. So we use custom mesh assets with their indices broken up into UV islands. So we do the tests I mentioned previously for figuring out what the UV islands are within the mesh, and then we store some reference information to those in these custom assets. We pre-transform all of our positions into world space. This means that at runtime, when we're generating the mesh, we don't have to do a matrix transform on every vertex. And we sort the vertex buffers by UV islands themselves. What this allows us to do is when we're at the phase of triangle culling for the generated mesh, if the island itself, if its bounding box is completely within the sphere, then we can just do a wholesale copy that's a lot faster than having to go through every triangle testing if it's inside or outside of the sphere. And finally, we also calculate the UV and world space bounds per island and store those with the reference information as well, so that we're not having to calculate that every time at runtime. And of course, profiling. This is a good example of the type of code that has fairly small code footprint. There isn't a huge amount of it, and it's generally very small chunks of code. But these small chunks of code are run many thousands of times. So if we can improve even the smallest piece of it, there's generally some pretty good gains to be made there. And we make fairly good use of hash sets and dictionaries and things like that for mapping during the generation process. And they all have different qualities and performance profiles as well. So being able to look at those and figure out what the best case is very important. And finally, we run the splat mesh generation off of the main thread. So as soon as the player initiates a teleport, we start to fade the screen to black. And as soon as the screen starts to fade, we kick off mesh generation in another thread. And generally, by the time the screen is fully black, the mesh generation has been complete so that we can begin fade in at the new location. So here is an example of this running with visualization. So as the player teleports around the scene, you can see the splat mesh volume is being generated, visualized here, color-coded with the separate islands, and those expanding out into the UV layout so that you can see what that actually looks like. And so it works. But now splats disappear after teleporting. Because we're generating this local splat mesh volume around the player, and the texture is only for that geometry. Every time the player teleports, we end up with a new mesh, and obviously now the texture is invalid. And that's not great. We want to be able to keep splats all around the level so the player can move around and cause chaos, basically. So this is where the splat cache comes in. We have light map UVs for all of our objects. Our game uses light mapping. And so for the majority of geometry in a scene, we already have a layout where all of that is uniquely unwrapped. So we can probably use that. So we're going to store all of our scene splat data in large textures. Remember, these aren't what we're updating during gameplay, and these aren't what are being read when we're rendering splats. They're simply a way for storing our data as the player moves around the scene. So the way this works is when a player teleports, the first thing that we do is we write out the existing local splat data to the splat cache. We then generate a new splat mesh for the new location that the player has teleported to, and then we read back from the splat cache for that new mesh. So what about beyond 10 meters? Can we bake splat shading? The 10 meters is pretty far from the player, so resolution is less important. And we're already using a splat cache to represent the splat data for the entire scene. So maybe we can also bake splats for the entire scene as well, using a similar approach. And so shaders beyond 10 meters blend baked splats with a single texture read. So they just simply read from the baked texture and then mix that in with whatever they're doing in the fragment shader for their surface. And then the splat mesh shader itself fades at the 10-meter boundary. So basically you get a crossfade between the dynamic splats from the splat volume and the baked splats for everything beyond. So packing 8 parameters into a single texture, because remember we wanted to try and get down from those 2 textures for our splat data to 1. So what we ended up using was a single R32 unsigned integer texture. And you can see in the diagram here how we basically allocated bits within those 32 bits to all of our 8 parameters. So persistent SDF now just uses 4 bits, the dynamic SDF uses 6, thickness uses 3, wetness uses 2, and then we use 565 for the color and a single bit for alpha. And so bitwise operators are supported in GLES 3, but in my tests, they're generally quite a bit slower than arithmetic equivalents. So when it comes time to packing and unpacking, generally, if you can use arithmetic to do that, it's better. And for sanity, we wrote a collection of macros for doing this encoding and decoding, but also in a manner that allowed us to have it defined for each of the parameters that we wanted to pack. That represented how many bits we wanted to allocate. And so all we had to ever do to change the bit depth for each parameter was simply update a single define for that parameter. And that was super useful during development because it allowed us to really see which data needed more precision than others. And this is how we ended up with this layout within the 32 bits. Unfortunately, though, bit packing means no hardware filtering, which is not fantastic. So how do we get around this? So the issue is that hardware filters textures at the component level, which makes sense. You have red, green, blue, alpha, each is a number. You're simply interpolating between those two. If those numbers aren't actually numbers themselves, but the result of several smaller amounts of data packed into them, then the end result is not going to be equivalent to the interpolation between those individual parameters. So can we filter manually in the shader? And the answer is yes. We can use things like gather red, which will return a vector that has the 4 samples that would be used for bilinear filtering. And then we can just unpack those manually and do the interpolation ourselves. And without any other option, this is definitely fast enough to be viable. It's certainly not cheap, but if you have no other option, this is definitely something that you can do and works. In our case, of course, it requires 4 unpacks. That's 32 parameters, and then 6 interpolations just to get the starting value that we then would use for shading. So definitely not cheap. And probably the worst part about this is, aside from anything else, we still can't use mipmaps. So aside from the quality issues with that, it of course then means that we don't get some of the performance benefits from the decreased bandwidth of reading lower mipmaps that are farther away. So that's not great. So the way that we get around this is what we call the splat texture resolve, and this goes hand in hand with the decoupled update. So as mentioned before, we could take a look at maybe not doing our update every single frame. And it turns out that our splats don't move. They basically become into existence when a splattable object collides with another, or when the player does some kind of power-based thing that results in splats. And so generally there's always things that are running at frame rate that are happening at the same time. So particle systems and other visual effects. And so a latency of potentially 2 frames for the splat appearing from when it should technically appear is actually not that bad. Was not really noticeable to the player in our tests. So that means technically we have 2 extra frames now. So what can we do with those? And the answer is our resolve. So we go back to 2 textures. However, we now use 2 16-bit textures. So those 2 16-bit textures essentially has the same bandwidth requirements as the single 32-bit texture, which is good. And of course, this means that we now get our hardware filtering and bitmaps back, which is really good. So resolved textures are 565, and the problem with that, of course, is before we had RGBA, now we only have RGB, so we're sacrificing 2 parameters. However, it turns out this wasn't actually an issue, because the distinction between persistent and dynamic SDFs is only really needed during the update phase, not at shading. So we need to be able to have 2 separate layers for a persistent and dynamic SDF when we update, because the dynamic SDF should be able to subtract the persistent SDF, and the dynamic SDF needs to be able to evaporate. But when it comes time for shading, all we're actually doing is creating a mask from the silhouette of those 2 SDFs combined together. So we can just do that ourselves in the resolve. So we take the min of the persistence in the dynamic SDF and store that in the red channel of our first 565 texture. And then, of course, just store wetness and thickness in the green and blue. And so for the second 565 texture, we just use that for the color of the substance. At this point, we've got down to only having 1 bit for alpha. And this was a result of, by the end of development, most of the substances really fell into a very small range of opacity. And so 1 bit ended up being fine, and we just basically made a substance either fully opaque or a certain constant transparent level. And it turned out that all of the substances that had this transparent quality to them were generally wet. So we can get rid of the alpha channel altogether and just infer that from the wetness parameter when it comes to time to shade. So the splat texture update. Before we were using a fragment shader, remember, and basically rendering the object itself. Now we just use a single compute shader. So the great thing about this, of course, is we don't require multiple passes. We can just iterate over the entire texture and calculate all of the updates. And we can also do dilation in line and use things like group share to speed that up and some of the other processes. The unfortunate thing, of course, is that compute doesn't have access to geometry. So whereas when we were running in the fragment shader, you would just calculate the world space position in the vertex shader, and then in the fragment shader, we would have access to that. In the compute shader, we don't have any of that information available. So what we now do is we store our world space positions in a floating point texture, and we just generate that along with the splat mesh volume when the player teleports. And a nice side effect of this is that when we generate this texture, if we dilate the position texture itself, when we're running our compute shader to do updates on the splat textures, we essentially get dilation for free because all of the splat updates are based on the positions, and the position texture itself is dilated. So those pixels just essentially get updated as if they were the same undilated ones. And we have an extra channel here. So we're using RGB for the XYZ of the world space, but then we still have an alpha component left. And so for that, we also pack some more data in there. So we store things like the movable geometry ID, which is used for doing the splat culling for movable objects. And we also actually store the dilation XY offsets there as well, so that if we ever need to dilate some textures outside of the compute shader, we have access to that and can do that with 2 texture reads instead of multiple passes. So the final implementation details. So on teleport, first thing we do is write local splats to the splat cache. We then bake local splat shading. So we essentially just run a simplified version of the splat shader itself. We then generate the new splat mesh that's 10 meters around the player. We bake out world space positions for that new mesh to the floating point texture. And then finally, we read local splats back from the cache into the local splat textures for that new mesh. And in our update loop on frame 1, we dispatch the compute shader that does the actual update of the splat textures. So this just simply reads all of the new splats that have been submitted, does min, and then finally packs the data and performs dilation. And then on frame 2, we do the splat texture resolve. So we have another shader that basically unpacks the data from the packed texture, combines the persistent and dynamic SDFs, and then outputs to those 2 16-bit textures via MRT. And then when it comes to rendering, we now just have a single mesh that we render. We render this at the end of the opaque draw calls using hardware blending. We have depth test and write enabled so that we can gain any benefits from that kind of pre-pass. And in our very specific case, we found that clip actually had a pretty significant performance boost for us. This is generally not advisable in most other instances because it takes away some of the depth optimizations. But in this very specific case, it actually helped out. We already know that this particular mesh is going to be in front of everything else. We don't really need to worry about that so much. And the amount of cost of the actual shading itself is fairly heavy. So being able to early out of that provided quite a decent boost. And finally, the splats themselves are actually anti-aliased as well. So for that, when we're generating the mask for the splats from the SDFs, we use F-width to figure out the gradient at the kind of screen space level. And that gives us a nice smooth anti-aliased edge around the silhouette. So that was my talk. Thank you very much for listening. I hope it's been informative. If you want to reach out, my email and Twitter are below. And of course, if you want any more information, check out owlchemylabs.com.